Hello everybody and welcome to my video. During the course of this video today, I'll be demonstrating how to exploit VulnServer with a buffer overflow. In order to have an environment set up to do this, I recommend installing Server 2016, running the commands you will see on my notepad in front of you. From here, install VulnServer onto the Windows 2016 server and test your connectivity between, I assume, your Kali Linux machine and the Windows Server machine. Be aware there is a lot of inbuilt security mechanisms for Server 2016 which you will need to disable, and as you see, these are all labelled on the document. So once you have this established, I recommend, if you're not already running a Server 2016 build, you might want to put Netcat on it to enable your testing between your sessions, just to make sure everything's flowing as it should. But you'll also need to install Immunity Debugger, Chrome, and whatnot, just to essentially assist you with this exercise. So from here, what I'm going to do is take you back to my Kali machine. As you'll see, this is my normal Kali environment. I always have it open with 4 windows. One where I'm running Netcat looking for my return shell, and up here I'll have the address to my code. Down here I was running sudo config before. I've been tinkering a lot with my IP settings, and I was reconfirming my IP address. And over this way, you'll see I have been generating some shellcode. So I'll bring this across, and you'll see that I've ran this command down here, which is my shellcode, to essentially generate this buffer overflow. What I'll do now is a quick demonstration of what the end result should look like. So up the top here I have my code. So I keep everything in a templates folder, and I go through a very distinct process of going about this. I'll quickly actually show you the code just so you have some sort of awareness. Just a quick talk through. I'm using Python 3. These are the required modules I'm importing. Sys, socket, struct. That's my Kali machine. Actually, no, that's not my Kali machine. That's the server machine. This is set up to essentially talk straight to that VulnServer using the trun commands. These will be talked about later. As you'll see here, I have my shellcode I've generated with MSF Venom. Importing struct allows you to import essentially variables without having to worry about doing the reverse little endian format, which can save you a little bit of time. Down to this variable, the variable shellcode. I've previously fuzzed this and determined it's 2003 bytes until I hit the EIP. I've then essentially placed in my return address, which is this up here. I've then added some padding in the forms of NOPs, or as you'll see here, it's represented in hexadecimal, and I've added 10 of them. I've then pointed back to my overflow variable, which contains my shellcode. So, cutting down to here, essentially this the socket here, that's just initiating the IPv4 connection. I've then added some print statements below, just so if the program fails at any point, I understand where it's failed. Then you'll see back there as well sconnect. That goes back to the top to the previously defined host and port variables. The send, that is sending the trunk commands, which I worked out previously by conducting spiking. And then I have the other statement there, which lets me know that everything's been sent across, and then it'll close. And if any of these things aren't met, I automatically get the error connecting to server. So I'll save this again one more time. And I'm going to fire off this exploit after I can confirm that I have VulnServer working. So you won't be able to see, but whenever you run VulnServer, you need to run this in administrator mode. It's also the same with when you run Immunity Debugger. Run as administrator. Doesn't look like nothing happened. Ah, it was already running, so I'll head back. And I'm about to launch my exploit, but before I do so, I'm going to ensure I have my Netcat listener listening. Yep, so that's listening on port 444. We'll move back across. As you'll see, I've gone through all those processes. Everything appears to be sent successfully, and I'm going to come back across here, and as you'll see, I've now got a shell on my Windows server. Hey everybody, welcome back. Continuing off, the first thing we need to do to compromise VulnServer is something called spiking. What spiking is going to do is essentially it's going to flood the server with commands until we can find really a vulnerable command. In order to determine which commands we can actually send to VulnServer, I've connected, if you look up at the screen, with Netcat to my Server 2016 machine, which is hosting VulnServer. Essentially, the first thing that happened is I got this header back here, which was welcome to VulnServer, and nothing else. I then hit enter to try and interact with it, got unknown command, ran help, unknown command, ran capital help, and it gave me this list of commands. From here, I've used a tool called generic send TCP. Generic send TCP. Essentially, what this tool does is it floods with TCP packets. If you see down here, I've actually ran a capture while I did this with TCP dump, and you'll see that the flood of connections by TCP packets, which would contain the header specified in your spike script. So if I open up this spiking script, you can see what it's doing as it sends it across the network. The main string that's it's sending across is stats. So I'll run this now. So you have the generic send TCP to this host at this port, and the 00 is just the parameters that you need to use when using this tool. So as you see, that's started essentially sending a whole heap of TCP requests on port 999 containing that stats field. If I come across back to VulnServer, let me just bring this across. Yeah, you'll see it's eventually failed, but I actually neglected to show you here, but in Immunity Debugger, when you run this, it actually doesn't error out at all. It just keeps going and going. Essentially what happens is the stats field doesn't trigger a problem. What we're going to do now is change that stats field to a command I know is vulnerable and try again. So coming back to my script, I'm going to change the stats command to trun. So that's been changed. Now what's going to happen is it's going to connect and essentially start seeing that trun command. And I know from essentially conducting this activity before the video that that is a vulnerable command. I'll open this up in as administrator. See, that's spawned this. Actually, we'll get rid of that old one and we'll open up a brand new one. We'll then open up Immunity Debugger as administrator, and then we're going to go and attach VulnServer. Attach. After you've attached it to VulnServer, you need to press play, and you can see that the program is now running. I'm then going to come back to Kali, and I'm going to launch this. As you'll see, that's now sending those TCP packets across on port 909 containing the stats field, and it has crashed in Immunity Debugger. As you see up top here, the EIP has been overridden by A's, so that's part of what the send generic TCP does, and yeah, pretty much all the other key fields have been overridden. So from that, we've been able to essentially control the extended instruction pointer. We now actively know that we can essentially exploit this program. What will go on after this is how we now go about fuzzing to determine exactly how many bytes we need to send across to crash the server. Hey everybody, welcome back. I'm just going to quickly walk you through this code. As you'll see, I'm at the stage where I'm about to fuzz a VulnServer. So as you'll see, I've imported Python. Correction, I'm using Python. I've imported these modules for my program. I've specified the buffer variable, which is going to send 100 A's in increments. So as you'll see in this loop, it's going to continuously try to send 100 A's, and it's going to increment every time until it gets to the point where it's going to crash the program. Just a heads up in advance, this is a bit unstable, and I'll probably end up killing the program. What we're actually going to be doing as well is we'll know in Immunity Debugger when the program stops. So I've gone ahead and set that up, and I'm going to launch this exploit now. So here we go. Let's go back to Immunity Debugger. You see everything is working fine like it should. The program is still running, and we're just waiting for it to get to the point. As you see, it is incrementing, and there we go. We've initiated crash. So I'll come back across here, and as you can see, it's crashed the program at around 2,500 bytes. So fuzzing crash at 2,500 bytes. Hey guys, welcome back again. As I ended off last video, from here we need to move on with finding the offset. So I've made this Python script, and the first thing we need to do, essentially even before we make this script, is we need to essentially generate this string value, which is the offset. So I'm going to head back to Kali. So let's just to the side. One moment, guys. And as you'll see down here, I have actually used a tool called pattern create, which is in Ruby, and I've specified that we want a length of 3000, and this generates the string value with random numbers. You're probably asking, why have I done 3000? As you remember in the fuzzing, the program crashed, I believe, at 2,300 bytes. So by essentially with this string, I think we're sending across 3,000 bytes to essentially get some visibility as to where exactly in the memory stack some items are sitting. So I've already made this script. I'm just going to quickly modify it so I have the correct address. So this is all set up now. I'm going to head back to Community Debugger. So save this, go back to Windows. Guys, unfortunately with this exercise you just have to keep opening and closing this, so best embrace it. Attach VulnServer, initiate, so make sure it's running, so press play, head back to Kalu, and I'm going to run the find offset script. So that's ran. We've crashed the program, so we'll look down here. Community debugger has been paused, and hey everybody, continuing on. So as you will see, after we've launched that offset script, all the variables for the 3000 byte string, send that across, and essentially it's overwritten all of the stack. So yeah, if we see here, we initiate the trun, then the offset variable, that's all going through. Keep going down. Let's have in the EIP, and really all we care about now is this EIP address. We know that command's overridden everything it needed in the stack. What we've now determined is this address. So what we can do is we need to copy this address down, essentially for later use. And what we're going to do is we're going to input it into a tool called pattern. I'll show you down here. Pattern offset Ruby. So as you see, it's part of Metasploit. Now, what happens in here is because we know the address of where the EIP sits, we specify this address, and it's gonna doing its thing, tell us exactly at what byte that EIP is. So I've ran this command already, and I've specified the length 3000 bytes. I've told it where in Immunity Debugger we see the EIP address, and it's told me back that yeah, that's this offset in that number. So from here we need to remember this and take it down. We can now go into controlling the EIP and essentially putting the data we want into that offset. So and that's that. The next thing that we're going to go on with, which you can see back across here, is 3. is overriding the EIP. So as you'll see in this script I've made, let me just bring it down a bit. What we want to test is to see essentially where that EIP is falling and if we can overwrite it. So what we've done is we've determined that we can send that if we send the 2003 in the other video it was the string figure. We've replaced that and changed it to just straight up A's for ease of use. Keeping in mind when you do look at A's in the Immunity Debugger, they come across in hex, so that's going to come across as 4.1. And from here, what we should see in Immunity Debugger is a whole lot of 4.1s or A's, and then only 4 B's or 4 2's in hex. So obviously this is quite a simple script. I'm just going to make that quick adjustment back to my Windows machine. 213. I'm going to save this. Save this, close it down. Once again, we'll go back to Immunity Debugger and VulnServer and run as administrator. It's just the most monotonous part, but also very necessary. File, attach, VulnServer, attach. And we'll have this running. So here we go, let's run the script. The script is ran. As you'll see, it's crashed Immunity Debugger, or it's Immunity Debugger's had an access violation, hasn't crashed it, it's crashed the other program. And we'll scroll up here and we'll see exactly what we want. So I didn't go over the stack, but if you print off a picture, you will see that the extended base pointer sits above the extended instruction pointer, so the EBP sits above the EIP in the stack. So all we really need to do is come across here, and we want to just like verify that everything is exactly where it should be. So let me go follow this in the stack. So follow that in the dump. Okay, so as you'll see here, yeah, I followed that in the dump, so I've right clicked on EBX, and what we can see here is all of our A's coming across as 4.1 in hex, and then we can also see our 4 2's, which are our B's, coming across. So inside here, our 4 B's have essentially sat right where we want, controlling the EIP, which is the instruction pointer or the return address. So from now we can essentially make the conclusion that yeah, we've controlled this adequately. We have essentially the right figures, and we're now positioned to generate our shell code. Hey guys, welcome back. This is the next phase, which is essentially determining the bad characters for our exploit. So what we need to determine is essentially what characters are going to make the essentially program malfunction. All we need to realize is that certain characters will essentially do different things to a program. For example, X4E could have a completely different function at that point in the stack for a program that's running. So you need to be cognizant that when you are reviewing this shortly, that things may not be where they seem, and everything really should read as it is here. As you see in my code up here, I've left in the null byte. For those of you who don't know that, essentially the hexadecimal slash x-ray 00 is a uniformly known bad character, so you can always just go ahead and blow that away from your scripts, or when you're about to start the bad character process. So cut that away. There's a good resource to essentially help you build this for your script, and that resource is this website here, Bulb Security Finding Bad Characters with Immunity Debugger. And as you can see here, all we need to do is copy this and dump it straight into your script. So as you'll see here, it keeps the null byte. Get rid of that straight away, and essentially we'll go back to my script and I'll explain to you what's happening. So no real change here, but as you'll see, my buffer, I then put B to where the EIP is going to be controlled, and then I want to see what bad characters are going to really wreck my shellcode when I run it through the program. So everything else below here is pretty much the same as you've seen in my last 3 scripts, and I'm just going to save this and fire it up. I've set up immunity and VulnServer already, so it's as simple now as running this. So we'll head across to Immunity Debugger. As you'll see down here, it has pause. So just let me drag this down. So yeah, as you can see there, it has paused, and that was the desired result. So as you'll see here, we really expected the A's in the script prior are where they should be, the EIPs staying the same address, but what we want to do is essentially see in the field after where the bad characters may lie. So I'm going to head across to ESP, and I'm going to follow in the stack direction, follow in the dump. Alright, so as you'll see here, let me just drag this down a bit. This is the dump, as they say. You can see all the A's. You're coming down, you'll see our 4 B's, and then you'll see our bad characters. Well, you won't see bad characters because there's none for this program, but you need to be cognizant of the fact later, especially when you're doing OSCP and the exam, there will be bad characters you need to annotate and be wary of. So as you see here, everything is as it should. It's just straight up counting in hex as you would normally. 1 through to 9, 0A, 0B, 0C, 0D, 0E, through to F, and all the way through. So the key takeaway from here is that with this program, the only bad character was the null byte. So all we need to do is remember that. But yeah, be specifically wary in the future. Even go and have a bit of a read on this. I'm not touching on it for very long, but finding bad. There guys, from here we're going to start building out the final phase of the exploit, which is essentially putting some additional command into the position of the extended instruction pointer. As you'll see here, this is the return address I've determined, which I'll take you through in a sec of how we came across that. Everything else in this code is pretty normal. If you want to copy it down, by all means. So I'll head back to Winows Server, and I'm just going to bring up this little cheat sheet of the process of things we need to do. So you're going to need to install the Mono module into Immunity Debugger. you can work this out, it's pretty easy. And what you're going to need to do from here is essentially, if you run the Mono modules command, it'll tell you these modules which are loaded by the program. As you'll see, it's this ESS func.dll, and that's the return address as to where it is, and it's essentially a jump point, jump ESP. So if you're already familiar with the new shellcode, you'll know what that means. For those of you that don't, essentially we can import this as essentially the point of code, which is the address directly before we start sending our own shellcode, which we'll craft shortly. If you run the command as you will see here, the mono find tacs xff tac e4 xe4, what that will do is xff/e4 xe4 is jump ESP. You can play with this in NASM shell if you so feel to. It's essentially just another NASM shell is another resource you guys will definitely have to use with OSCP. No, essentially, yeah, for converting assembly code commands into hexadecimal. So yeah, jump ESP is FFE4, and what we can do is we'll paste this in for demonstration purposes. As you see, it's already, it gave me the error, but it has worked. What you need to essentially recognize here is these are the essentially the memory protections. You guys will need to familiarize with these, but I don't know, the main one I typically notice is ASLR. And essentially what that is randomization for memory addresses. To be very vague, and that's false across all the other ones, which are also false. So that essentially sets the stage for us to use ESS func.dll, and we'll be hooking onto that. As you'll see up here, we have the jump ESP at this return address. So we need to take note of this return address because that is going to be essentially our new EIP overriding the 4 Bs. So make note of this address, and we'll head back to our Kali machine and I'll show you my code. So as you can see, yeah, my code's are good to go, and one thing I failed to tell you here is you're going to need to set a breakpoint. This is just a way to validate that the code is working. So we'll minimize. So you come across this. Let me just scroll up, please, and you'll see that it's this blacky blue sort of logo. Click on that, put in your return address, hit OK. You'll see it's that FFE4 jump ESP. Use F2 to make the breakpoint. See it's all good now. Start the program. Go back to Kali, and I'm going to launch this code. and success, as you'll see. To wrap this up, as you'll see, this is the final iteration of my script in order to exploit the buffer overflow. So, as you'll see here, Python, I've imported struct, which is a little tool for mitigating the need to use little endian format. As you'll see here, I've just made a variable struct.pack, little endian less than, so it doesn't really matter. I've then made my shellcode, a plus the return address, which, as you'll know, is the extended instruction pointer, which is this address, which we determined previously. I've then added some nops, which are like shellcode padding. I've added 10 of those, and I've added my overflow, which is the shellcode itself, which contains the exploit and will give me the shellback. I've then added a few little commands just so if it does fail, I know exactly where it's failing. So nothing too significant here. All I need to do now is save this, close it down. To actually generate the shellcode, I didn't cover, so it's quite simple. All you need to do is use MSF Venom, and this is all the syntax I've used. MSF Venom, TACP, Windows, shell reverse. Back to my calling machine. Localhost is my calling machine. The port I want to connect in on. Exit function equals thread. My type is Python. Select script type x86 for Windows kernel, and TACP is my bad characters. As you remember a bit earlier on, we determined that because it's a vulnerable application, there was no bad characters, and all we have to do is select a null byte. I've then also added TACV, which is variable, and I've called it overflow, so the script actually prints it all out for you, which is nice. Then all I'm going to simply do is go back up to here. I'm going to set my Netcat, so that's listening on port 5555, and I'm going to launch exploit. After I've made sure VulnServer is running, so it's all humming, and with a bit of luck I'll pop a shell. And success.